continue now. It's a pleasure for me to present my PhD student, Darío Asa from Buenos Aires. He's going to talk about foliations, Poisson structures, and residues.
Thank you very much, Matthias. So I will start by thanking the organizers, and in particular Matthias and Federico, who are my advisors, and also congratulating Fernando, obviously. And well, the talk will be of foliations, Poisson structures, and residues. So let's begin. Let me begin with an overview of the subject. So I will later define most of the things carefully, but let's begin with an overview of what we thought and our results. So first, you have a complex Poisson manifold of rank R on this side, and the singularities of a complex Poisson manifold are not just a subspace, but actually they are a stratification of subspaces, because you can look at how singular the Poisson bracket is on each point. And in the year 2010, these two mathematicians, Marco Gualtieri and Brent Pim, defined Poisson residues, which worked in this fashion. You take as an input a Poisson line bundle, which is like a module over the Poisson manifold, and an integer, and the output is this thing, this multi-derivation supported on the singular locus. Actually, when you pick the integer value, you get different multi-derivations on different singular locus. And on the other side of the picture, I will begin by saying some things about singular foliations. So if F is a singular foliation of rank K, then the singularities are the usual singular locus, the points where the normal sheaf fails to be locally free, and U is the regular open subset. And in the year 1972, Baum and Bott defined famous Baum-Bott residues, which work in this other different way. The input is a characteristic class of degree greater than the codimension, and the output is a relative cohomology class relative to the open subset where the foliation is regular. And well, there's this claim I tell you that every Poisson manifold has an associated symplectic foliation, and the question is, can we relate these two residues in any way? And well, the difficult part is that they live in two very different spaces. We began thinking about this question, looking at concrete examples on P3, and we were motivated by this question being posed on the paper by Marco Gualtieri and Brent Pim. And so I will tell you what our main results were on these directions. So if you take a complex Poisson manifold without content and of rank R, I will later define all of these things, you don't worry about that, but you take a Poisson manifold and some non-degeneracy conditions, and if Z is an irreducible and reduced component of the singular locus of dimension 2R minus 1, one less than the total rank of the Poisson bracket, then the vanishing of Gualtieri-Pim's residue along this component implies the vanishing of one of Baum-Bott's residues. Gualtieri-Pim's residue is the one associated to the canonical Poisson line bundle, and Baum-Bott's residues is the one associated with this Chern class. And on the other hand, we have like partial converse to this result that we managed to get only on codimension 1 foliations. So if X is an almost regular complex Poisson manifold, and in this case, the dimension of the manifold is 2R plus 1, meaning that the symplectic foliation is of codimension 1. And if you pick an irreducible component of the singular locus of codimension 2, then if the manifold is Fano, we can get that if the Baum-Bott's residue vanishes associated with this polynomial, the second power of the first Chern class, then Gualtieri-Pim's residue vanishes on the same component. So in the first theorem, the hypothesis we need is that the component must be reduced, and in the second one, we got that we needed the variety to be final. So I will explain why these theorems hold. And so what is a Poisson structure first? So a complex Poisson manifold is a complex manifold with a bivector field that satisfies this integrability condition. The bracket with itself, the Schouten-Nienhaus bracket with itself must vanish. And that's an integrability condition on the Poisson, on the bivector. Whenever you have a Poisson structure, this amounts to having a Lie bracket on the sheaf of functions. So you actually have a sheaf of Poisson algebras. And the bivector has rank R when R is the greatest number you can take a power of pi that doesn't vanish. Examples of Poisson brackets are, well, every symplectic manifold is a Poisson manifold, and in particular, holomorphic symplectic manifolds are holomorphic Poisson structures. The dual of Lie algebras have a Poisson structure which goes by the name of Constant and Kirillov, and any bivector on any surface will be integrable because the trivector P against P has to vanish. But another example, which was the one we began working with, were Poisson structures on P3. And on P3, a Poisson structure amounts to having a foliation of degree 2. The one form has to be of degree 4, possibly with content. And how does that work? Well, you pick a Poisson structure, which is a bivector, and, well, you take a section of the canonical sheaf, and you contract them, and then you get a one form twisted with the anticanonical sheaf. And under that operation, if the bracket was integrable, then the one form will be integrable. Yeah? But the one form may have content, may have singularities of codimension greater than 2, lower than 2. So how does a Poisson manifold get a symplectic foliation? So whenever you have a local holomorphic function on a Poisson manifold, you have a Hamiltonian vector field attached to it, which is just the contraction of the bivector with the one form D of F. And at the same time, you have Poisson vector fields on a Poisson manifold, which are just local holomorphic vector fields such that the Lie derivative of pi with respect to x is 0. Hamiltonian vector fields are always Poisson vector fields, but not necessarily the opposite. And the difference between these two kinds of vector fields is important in the Poisson community. And this equation here holds. And because of this equation, you can see that Hamiltonian vector fields form an integrable distribution. The integrable subsheaf of Tx generated by Hamiltonian vector fields is what we will call the symplectic foliation. And we will write it Fsim. So in which sense is this a foliation? I mean, I want to clarify some aspects of this. Well, for us, a foliation will just be an integrable distribution. Yeah? And in this sense, it's clear that what we defined is a foliation. The singular locus is, as usually, the points where the normal sheaf is not locally free. The regular open subset will be called U. And I want to talk about the saturation of a foliation. When is a foliation saturated? So a foliation is saturated if any section of the foliation outside of the singularities extends to a foliation on all of the, to a section on all of the open subset B. Being saturated is the same as the normal sheaf being torsion-free, and it's the same as the sheaf being reflexive and the singularities having codimension 2. I think Cesar talked about this on his talk. And so the thing I wanted to say is that symplectic foliations are in general not saturated. And they are not saturated because of the two reasons. You can have singularities of codimension 1, but you can also have symplectic foliations which have singularities of codimension 2 or 3 or greater, but they are not saturated. Since they are not saturated, you can't do this thing where you dualize the distribution and you think about it in terms of forms, because when you do that, you get a different distribution when you annihilate that form. You get the saturation, actually. For us, a leaf will be a maximal connected integral subvariety. So we are here focusing on all integral subvarieties and not only on the ones on the regular locus. Because of this, all of the space X has a unique partition into leaves for any singular foliation. And the reason why we call the symplectic foliations is that the leaves are always symplectic submanifolds, possibly singular, of X. And therefore, they are always even dimensional. So I got an example here. It's a formula for a Poisson bracket there. And with that Poisson bracket, the symplectic foliation is generated by the Hamiltonian vector fields associated with the functions x1, x2, and x3 on C3. I will call those three vectors B1, B2, and B3. And they are not independent. It holds this relation between them. And it has to hold because the leaves have to be of dimension 2. I recall that they have to be of even dimension, so it cannot be a foliation by leaves of dimension 3. The singularities of these foliations are the three lines. However, this is not saturated because if you take the first vector I wrote there, the one that I call B1, and you divide it by x1, you get a vector field which does not vanish on the singularities, even though B1, B2, and B3, the three of them vanish on the singularities. Therefore, this vector field lives in the saturation, but does not live on the foliation, in symplectic foliation. And the leaves here are the two-dimensional regular leaves, and on the singularities, you just have points. So I will talk now about residues. And I will start with Poisson residues first. So whenever you have a Poisson manifold, a Poisson subspace is a subspace such that every Hamiltonian vector field is tangent to it. And we call a subspace a strong Poisson subspace if all of Poisson vector fields are tangent to that subspace. There are some strong Poisson subspaces that are the degeneracy loci of pi. And those are given by this equation. They are the zeros, the points where p to the power of k plus 1 vanishes. And this gives the stratification I was talking about before of the singular locus. You can think of X as being stratified by strong Poisson subspaces, and the lowest of them all is the points where the bivector vanishes, and the highest of them all will be the singularities of the bivector field. And the singularities of the bivector field coincide with the ones of the symplectic foliation. So the motivation for this, for the paper where they defined these Poisson residues was Bondal's conjecture. So I'm going to talk a little bit about that. So the degeneracy locus of degree 2k is the set of points such that through that point, the symplectic leaf has dimension at most 2k. Yeah? So the regular ones are the ones that have the highest rank. And on the singularities, you have this stratification. So Bondal's conjecture is the following. If X is a Fano Poisson manifold of rank R, then the 2k degeneracy locus has an irreducible component of dimension at least 2k plus 1 for all of the k's. And what does this mean? Well, since the leaf through a point P has to have dimension 2k, this means that you have like a continuum of symplectic leaves, you know, like a transverse direction to the symplectic leaves. So what is known about Bondal's conjecture? Well, in 1997, Polishuk proved the conjecture in dimension 3. And what he did was prove that if pi has rank R, then the singularities of the bivector have a component of at least dimension 2r minus 1. And the techniques involved here were Baum-Bott residues of the symplectic foliations. In 2010, Gualtieri and Pym proved the case of dimension 4 of the Bondal's conjecture, and the techniques involved here were Poisson residues, which they introduced, and also Poisson modules. Well, actually, Poisson modules in order to introduce Poisson residues. So I'm going to talk a little bit about Poisson modules, but just in the case of rank 1. What is a Poisson line bundle, which is what we need to define Poisson residues? So you pick a line bundle over a complex Poisson manifold, and a Poisson connection is a contravariant connection in the sense that it goes from L to the tangent shift tensor with L, such that it satisfies this Leibniz rule. And a Poisson line bundle is a pair of a line bundle with a flat Poisson connection. And it's flat in the usual sense that when you extend it, it is it composes with itself to 0. If you pick a Poisson line bundle and the local trivialization, we can write nabla applied to the section S in the following way. A vector field O times tensor with S. The vector field we get is what we will call the connection vector field of the Poisson line bundle associated to this trivialization. The connection is flat if and only if this is a Poisson vector field. And when it's a Poisson vector field, it has to be tangent to all of the degeneracy locus. The canonical example, the most important example here is that the canonical sheaf and the anticanonical sheaf also, they are both always Poisson line bundles. So I'm going to just tell you what the canonical sheaf Poisson line bundle structure is. If you take a section S of the canonical sheaf and you apply nabla to it, and then you contract it with a one form, this is what we usually write in this way, like contravariant derivative. And the formula for that is this one. You contract the section with the bivector, you then take the exterior derivative, and then you wedge with alpha. And this gives you a Poisson line bundle structure on the canonical sheaf. Its connection vector field is what in the Poisson geometry community is known as the modular vector field. So what are Poisson residues? So when you take a Poisson line bundle, its kth Walteri beam residue will be defined by this formula here. So you pick the connection vector field associated with the Poisson line bundle, and you take its wedge product with the kth power of pi, and then you restrict it to the kth degeneracy locus of the Poisson bivector. When you do that, it doesn't matter which section you choose. This always gives you a well-defined multi-derivation on this subspace. And it doesn't matter because the difference between the two different connection vector fields is always a Hamiltonian vector field. And therefore, the Hamiltonian vector field wedge product with pi to the chi will vanish in this subspace. So this is the definition of Walteri beam's residues. And one important fact about them is that they could provide an explanation for the dimensions appearing in Bondal's conjecture. If you could prove something like the following fact, an ample line bundle has always non-vanishing Walteri beam residues, then applying that fact to the canonical line bundle of a manifold, you would get that all of these spaces have to have dimension at least 2k plus 1. So what about bound-Bott residues of foliations? Well, we will start talking about a little bit of characteristic classes of foliations. So first of all, there's Bott's vanishing theorem, which is the following. You take a regular foliation of codimension Q, and then the Chern ring must vanish on degrees greater than the codimension, the Chern ring of the normal sheaf. Because of Bott's vanishing theorem, you can define characteristic classes for foliations, and you can define them in this way. If you fix a basic connection nabla and the unitary connection on both of on the normal sheaf of the foliation, well, then you get a well-defined morphism of complexes, well-defined up to homotopy, which is given by the following. You have first this complex WUQ, which is given by symmetric polynomials on the Chern classes and also on their conjugates, and an exterior algebra on H1 to HQ. And you mod out these two first pieces by an ideal given by the polynomials of degree greater than Q. If you define these degrees of here, meaning that all of the Chern classes will have 2i degree, and these ones will be odd, and you define this differential here and the differential 0 on the symmetric part, then this defines a complex and a differential graded algebra. And this over here, with the two connections you chose, defines a morphism to the RAM differential graded algebra. And it's a morphism of complexes. And it is well defined up to homotopy because if you choose two different connections, then in the usual sense where in the usual way where you show that the characteristic classes that do not depend on the connection. That way, you can get an homotopy between the two maps. So how can we talk about bound-Bott residues with this, or in this context, or in this way? Well, the Chern-Weil morphism also defines a morphism of complexes up to homotopy, and it goes from here, from the polynomial ring on Chern classes to the RAM algebra. And well, here the morphism is just you take a polynomial and then you evaluate it on the connection, and that gives you a form. And this is well defined again up to homotopy, because if you take two different connections, they are homotopy equivalent. So when F is a singular affiliation, you've got a commutative diagram in this way. If you first take the characteristic classes of the normal sheaf, and then you restrict it to the open subset, then it's the same as first projecting to this algebra and then taking this, the characteristic classes of the regular affiliation. This induces a morphism between the cones of the two maps, the one on the left and the one on the right. The cone of the map on the left has as classes in cohomology all of the polynomials of degree greater than the codimension. And when you apply in cohomology this map, the one that descends between here, you get something in the cone of this map, which is just the relative cohomology with respect to the open subset. And that's what we call bound-Bott residues. So there are some computations you can always do on bound-Bott, not always, but for instance, if the degree is just one more than the codimension, you can do this computation. You just, if the degree is just one more than the codimension, and the singularities have a dimension at most k minus 1, and if you pick all of the irreducible components of the singular locus of dimension exactly k minus 1, then this relative cohomology is the same, well, as Borel-Moore homology of the singular locus, but that always, in the case set is compatible, that's just the singular homology, the usual singular homology, and that's always generated by these irreducible components. Because of that, you can write bound-Bott's residue as a sum of numbers times the classes of these irreducible components. Those are numbers, complex numbers. For minimum degree, meaning this n minus k plus 1, you've got an algorithm to compute these residues, and that algorithm was already described on bound-Bott's original paper. So I'm going to talk now about our results. I've got first to talk about some definitions. A Poisson structure of rank R has content if the singular locus has codimension 1 on X. That's a similar definition to the usual in foliation theory. And a Poisson structure is almost regular if it has rank R, meaning that the symplectic foliation will have rank 2R, and the dimension is exactly 2R plus 1. So the symplectic foliation is of codimension 1, and pi has no content. Well, there's the usual definition of a Kupka point of a foliation F. So if you have a foliation given by a differential one form, twist differential one form, you can point a Kupka point if it's a singular point of the foliation, but the derivative of the differential form is non-zero at that point. Its Kupka locus will just be the closure of all the Kupka points. And we got first this key fact, which is the one that allows us to relate both of the worlds, the Poisson and the foliation world. And this key fact tells us the following, that Poisson manifold of rank R without content, then Gualtieri-Pim's residue of the canonical bundle will vanish at a point if and only if that point is a non-Kupka point of the saturation of the symplectic foliation. So I will recall the results I talked about in the first slides, and I will then tell you a little bit about the proofs of these results. So on the first theorem, we have a complex Poisson manifold without content and of rank R, and an irreducible and reduced component of a singular locus of the Poisson structure of dimension 2R minus 1. And if the dimension of a singular locus is less than 2R minus 1, then if Gualtieri Pim's residue vanishes along that component, then this number, the number we had associated to the component set of the Poisson residue, will vanish too. And on the other hand, if the manifold is Fano and the structure is almost regular, meaning that it's of codimension 1, and Baum-Bott's residue vanishes along the component set, then Gualtieri Pim residues will vanish in that same component. Yeah? So let's talk a little bit about how we proved these theorems. Maybe the idea, because I'm almost running out of time. But let's talk about the idea of the first implication, but in the almost regular case. The general case is the same, but in the almost regular case, all of the ideas are present and the computations are a little bit easier. So if Gualtieri Pim's residue vanishes along a component set, then set is a non-Kupka component because of the key fact that we talked about. If we restrict to a transversal to set around the point P, then, well, our one form will be, because zeta is of codimension 2, will be just one form of this type. And we can use the algorithm for computing this residue. The algorithm was Baum-Bott's original algorithm for computing residue, and it's just local. It's local computations. So you can do it around this point and just restricting to this transversal. When you do that, you use that algorithm, the computation reduces to computing the coefficient corresponding to this form in the Taylor series expansion of this form I'm writing over here, where the b's are just the coefficients such that we can write the coordinates x1 and x2 as combinations of the coefficients of omega. Well, I didn't say this, but this form, since we restrict it to a transversal, will just have one isolated 0, and we can assume it to be 0, 0, the origin. And, well, that's why these functions B will exist. Now, since set is reduced, we can conclude that alpha 1 and alpha 2 will have to be 1 because the ideal defined by the A's will be reduced. And since alpha 1 and alpha 2 are 1, and set is a non-Kupka component, we have that the trace of this matrix A, I didn't actually say what the matrix A is, but it's, it's just the derivatives of the A's in a matrix, but this trace will be 0. Since this trace is 0, the determinant of a holomorphic matrix of functions is a holomorphic function, and the alpha 1 and alpha 2 are 0s, then this Baum-Bott residue vanishes. And what's the idea behind the other theorem? Well, so suppose that Gualtieri Pim residue does not vanish along this component set, then the component will be a Kupka component, and therefore we can use a linearization result, which I believe here is really famous, by Gomez-Mont and Linz-Neto, and we can reduce it, the whole computation to the case where the one form is given by px dy minus qy dx for p and q coprime integers. And when we compute its Baum-Bott residue, it's just this formula over here. And this formula will not be 0 since we are assuming the Kupka component to be a Kupka component. So this proves the other implication. The point where we used that the variety had to be Fano is because the symplectic foliation is always of anti-canonical degree, and the linearization result uses that the degree has to be an ample line bundle.
So here to apply Gomez-Mont and Linz-Neto, you need the Z to be Kupka at every single point, right?
Yes, but you need it to be a Kupka component. Yeah, and we are assuming that the residue does not vanish in the Kupka component.
At every point.
Yeah, that's what we are assuming, yeah. I can finish here, but I also had an example with me, which is, I actually wanted to show this example because it was the first example where we got the result, or we got what we wanted as a result. Since, we can start with a Poisson structure on P3 of this kind. And these Poisson structures are equivalent to the foliations, or its symplectic foliations. When you saturate them, they give you foliations of type L111111. These are what are called diagonal Poisson structures. If you take the singular locus, it's just a union, too many ones. It's just a union of 6 lines. And if you pick, for instance, the first line, this is the first computation we did, then Gualtieri beam's residues along that line is this number multiplied by this vector field, yeah? And Baumbach's residue associated to that line, the number of Baumbach's residue associated to that line, to that component, is this number over here. And you see there how the result works here in P3. I think I went too fast maybe, but well, that's all. Thanks.
Can you show again the main?
Yeah. Here.
So I kind of was confused. So where is this assumption that it vanishes nowhere?
Well, that's what maybe we wrote it not in the best way, but that's what we mean by this. Actually, if you're taking just an irreducible component, then the locus of points where it won't vanish is an open subset. So, as in the example, it won't vanish anywhere if it doesn't vanish on it won't vanish anywhere if it doesn't vanish on a point. But that's what we mean by the symbol.
Well, any other comment or question?
So do you believe in Monod conjecture?
Yeah, I personally do. Actually, I really do.
Every day of the week?
Every day of the week.
If there are no other comments or questions, let's thank Darío again.